Hello everyone, and welcome to another interesting lecture related to the Physical Pharmacy 1 module. This lecture is supposed to be given on Monday, the 16th of March 2020. The time of lecture is 11:30 to 12:20 according to the weekly timetable. So let's get started. In the previous lecture, we covered the most important information related to the solutions of non-electrolytes normally used in the pharmaceutical field. In this lecture, we are going to talk about another topic which is related to the solutions of electrolytes. So we normally in the pharmaceutical field we are using solutions of different materials, some of them solutions of non-electrolytes and the other are electrolytic solutions. Now the topics that will be covered in this lecture are the following. The first thing is the colligative properties of pharmaceutical electrolyte solutions and how can we compare the colligative properties of this type of solutions compared to the other type, which is the non-electrolyte solutions. Then the second topic will be the electrolytic dissociation. The third topic is drugs and ionization. The fourth topic will be a degree of dissociation. The fifth topic will be the activity and activity coefficients, followed by an interesting and important topic which is the ionic strength, and finally I will summarize the chapter in a very useful and summarized notes. As I have mentioned previously that the colligative properties of pharmaceutical solutions of non-electrolytes, they are depending on the number of molecules in the solution. Now for electrolytic solution is they are different from non-electrolytic solution. Now the number of the colligative properties are depending on the number of ions after the dissociation of the electrolyte in solution. So they notice that the colligative properties are deviating from the colligative properties of non-electrolyte solution. So for example, if we are talking about the osmotic pressure, the pi equals IRTC. The osmotic pressure pi is equal to the I, which is the what they call it the correction factor. So this is account for the deviation or irrational behavior of ionic solution, or the anomaly happens in the colligative properties of electrolytic solution. R is the gas constant, T the absolute temperature, and the C is the concentration of the solution. So according to this, for electrolytes, the colligative properties are normally depending on the number of ions formed in the solution after the dissociation of the electrolyte solute in the solution. Like for example, in this case, so the I value, the correction factor, is actually depending on the number of ions generated in the solution. If we are talking about sodium chloride, the I is approaching 2. For calcium carbonate is also 2. For potassium carbonate, the I will be 3, and so on. So depending on the number of ions generating in the solution, the I value will be depending on this number, and the correction of the osmotic pressure will happening this way. So it depends on the number of ions generated in the solution. Now in this slide I will talk about the electrolytic dissociation. So as you know that in the pharmaceutical field we are dealing with different compounds having different compositions or different natures. Now regarding the electrolytic dissociation, we do have quite a lot of compounds, as I said. Now as you can see in this slide, the first equation showed that the sodium chloride, even in the solid state, we put plus and minus signs above the Na and the Cl. This is an indication that sodium chloride, even in the solid state, it exists in the ionic form. So the ions are existing in the solid state. Now when we dissolve the sodium chloride in water, we will get the sodium ions and the chloride ions in the solution. So that's the dissociation of sodium chloride in water. Now if we talk about the hydrochloric acid, here the compound is in neutral in the pure or the original as hydrochloric acid compound, but when we dissolve the hydrochloric acid in water, then we'll get a hydronium ion and the chloride ion. So in this case we have complete dissociation of hydrochloric acid and sodium chloride in water, and that's why we call these compounds as strong electrolytes. So we have a variety of compounds in the they can be called as strong electrolytes such as sodium chloride and hydrochloric acid, sulfuric acid, and so on. On the other hand, if we look at the acetic acid in the third equation, we can see that there is an equilibrium sign in the equation. So when you dissolve the acetic acid in water, you will get partial hydrolysis of acetic acid to form the hydronium ion and the acetate. So what does that mean? It means that the acid will dissociate in the water to a certain extent and then will reach the equilibrium status. In this case, the dissociation will equal the formation of the acetic acid and the water, and this is called equilibrium state. So in this case we will have a weak electrolyte, which means that we are not dealing with a compound that's completely dissociating in water to give the ions. So that's the difference between the different materials. We do have strong electrolytes and weak electrolytes. Now if we are talking about the drugs and the ionization, again as mentioned before, the drugs are also compounds that could be existing in a strong electrolyte form or weak electrolytes, depending on the degree of ionization after the dissociation in water. So that's about the ionization or the dissociation. But I'd like to mention here that when we dissolve a drug in water, the drug become either cationic or anionic, depending on the type of drug and the nature and the chemical structure of the compound. And more specifically, if the drug has a basic group, like for example in this slide we do have the ammonium moiety in the structure, that will be proton weighted when dissolved in water to give the hydronium or the ammonium form in this case. So that's giving the cationic nature of the drug as ion. So in this case we do have cationic drugs and anionic drugs depending on the chemical structure of the compound. And this is one of the classification. The other classification, we do have the strong electrolytes and the weak electrolytes, and this is depending on what, on the degree of ionization of the compound in water. So these are examples of some drugs that are existing in the cationic form. You are required to find like 5 drugs existing in the anionic form after the dissociation. Okay, that's a homework. Now, as you know that in pharmacy we are not dealing with the drugs alone. So when we are making the formulation and we are fabricating the different dosage forms, we are using the active pharmaceutical ingredients, the APIs, and lots of other materials. We call these materials as excipients or non-active materials. Now these materials or these compounds are also subjected to the ionization. So excipients can be in the ionized form after the dissolution in water. So an example of these, in this slide, we do have the sodium lauryl sulfate, and this is belong to a class of compounds. We call them surfactants. So in this case we do have the anionic form of the surfactant, so it's existing in the anionic form, and then the cation is sodium. And another example is benzalkonium chloride. So we have here the reverse. So in this case the compound is in the cationic form, and the other compound is the chloride, which is the anion. So these are 2 examples of pharmaceutical excipients existing as ions in water. Both of them are excipients, belong to the class of surfactants, one existing in the anion form and the other in the cationic form. As I mentioned previously, that the difference between strong and weak electrolytes is based on the extent of ionization. Strong electrolytes are dissociating to high extent, while weak electrolytes are dissociating into lower extents. So that's the difference. What they found that the extent of ionization or dissociation is directly proportional to the conductance or the equivalent conductance. If we have more ionization, we'll get more conductance through the solution. I mean electrical conductance in this case. So by using the conductance, it's possible to measure the ionization. So for example, if we have a solution with complete ionization, that's the we'll get 100% conductance in this case, because we do have more ions. And if we get lower ionization, the conductance will be directly proportional to the degree of ionization. So in terms of the conductance, it's possible to measure the degree of ionization as it can be seen in this equation. So the alpha, which is the degree of dissociation, equal to the equivalent conductance at certain concentration divided by the equivalent conductance at infinite concentration, I mean infinite dilute concentration. So infinite dilute concentration is more likely the electrolyte will be dissociating completely. And this example showing you that if we have the electrical or the equivalent conductance for the partial ionization and the complete ionization, we can simply measure the degree of dissociation. So in this example, the equivalent conductance of acetic acid at 25 degrees centigrade and infinite dilution is 390.7 ohm, and then the equivalent conductance of 5.9 multiplied by 10 to the power minus 3 molar solution of acetic acid is 14.4 ohm. Now the question is, what is the degree of dissociation of acetic acid at this concentration? So as you can see in this example, that different concentrations have different dissociation. So it's a weak electrolyte. As you dilute the concentration of acetic acid, you will get more ionization of the acid. So in this case, the degree of ionization can be obtained by dividing the equivalent conductance of the acetic acid at the mentioned concentration 5.9 multiplied by 10 to the power minus 3 divided by the conductance at infinite dilute solution of acetic acid, and then we'll get the degree of dissociation, which is 0.037 in this case. Now another question could be asked, can we calculate the degree of dissociation using other method rather than the conductance or the equivalent conductance? So the answer for this question is yes. We can calculate the degree of dissociation by using another equations. So in this case, we are using the colligative properties, and one of these colligative properties, which is the freezing point depression. So depending on this method, we need to calculate the Van 't Hoff factor, which is the I, and this is equals this is equaling to the depression in the freezing point divided by the Kf, which is a constant, multiplied by the M, which is the molar concentration. So after calculating the I, we can calculate the degree of dissociation. So the degree of dissociation is I, which is Van 't Hoff factor minus 1, divided by V minus 1. The V is the number of ions generated in the solution. Like for example, if we have sodium chloride, so the V is 2, because we do have 2 ions generating in the solution. So by using these two equations, it's easily can be used for the calculation of the degree of ionization. And these two examples can show how to calculate this equation. So the first one is for acetic acid, which is weak electrolyte, and the second one for a strong electrolyte, which is ammonium chloride. So in this case, we can calculate the I in both cases by using the first equation, and then calculating the alpha, which is the degree of dissociation, by using the second equation. So that's all about how to calculate the degree of dissociation using the freezing point depression. Another important thing I want to mention: how can we judge that this is strong electrolyte or weak electrolyte or intermediate electrolyte based on the degree of dissociation? I mean, if we get like 0.5 degree of dissociation, can we classify it as strong electrolyte, intermediate electrolyte, or weak electrolyte? This is a homework for you. So I'd like you to search how can we decide what type of electrolyte we have depending on the degree of dissociation. Now, after covering the topic related to the degree of dissociation, we are going to move to another topic, and this topic is about activity, the activity and the activity coefficients. In the last chapter, I explained that for solutions of non-electrolytes, the number of particles or molecules inside the solution is actually proportional to the values of the colligative properties. So And as we have more particles, the values of the colligative properties are proportional um, to these particles. So that's in non-electrolyte solutions. Now, if we want to talk about electrolytic solutions, so for example, if we have strong electrolyte, so do we have the same relationship? Do we have the same direct proportional between the number of ions generated in the solution and the colligative properties or not? The answer for this question is it depends on what concentration do we have. Let's introduce an expression. We call it the activity. So what do we mean by the activity or the effective concentration? So the effective concentration or the activity is actually referring to the number of ions or the concentration of ions generated in the solution that's actually contributing to the colligative properties. Like for example, how many ions are in solution and these ions are actually contributing to the colligative properties, such as the depression in the like boiling point elevation, freezing point depression, and so on. So this is also depending on the concentration of the ions. So if we are talking about moderately concentrated and highly concentrated electrolytic solution, we will see that the activity or the effective concentration is less than the concentration of ions. So we have this number of ions, but actually the colligative properties, which is depending on the number of ions, is less than that of non-electrolytes, for example, considering we have the same number of particles in the solution. The reason for this is because in moderately or strong electrolytic solution we have some forces between the ions. We call these forces the electrostatic forces. So these forces, because the ions are closer to each other, will make the ions hindered or not behaving as free, and that's why it's not contributing completely to the value of the colligative properties. So that's the situation for the moderate or highly concentrated electrolytic solution. But in infinite dilution of electrolytic solution, and because the ions in this case are widely separated, so in this case what we have, the electrostatic forces are approximately absent in this case, and the ions are behaving as separate. So in this case each ion will contribute to the colligative properties, and in this case the activity is equal to the concentration, whether the concentration is molar concentration or molar concentration. So in this case, dividing the activity over the molar or the molar concentration will equals to 1. So the activity is equal to the concentration, and this is because we are dealing in infinite dilution and the ions are widely separated, so there is no electrostatic interactions or attractions. Now, as I mentioned in the previous slide, if we are dealing with the infinite dilution, then the activity equals to the concentration. I mean, all the ions in the solution will contribute to the properties of the solution, including the colligative properties. But then if we increase the concentration of the solution, in this case the ions will become closer to each other, and then the ratio of the activity to the concentration becomes less than unity, and then we can express this relationship as A over M equal to gamma m, which is the practical activity coefficient, and that's again because of the attraction forces between the ions in the solution. So A over m is not equal to unity, but instead it will equals to the gamma m, which is the practical activity coefficient. Okay, so in this case we have different expressions for the activity coefficient depending on what kind of concentration expression we are dealing with. So if we have the molar concentration, the activity equals to gamma m multiplied by the molar concentration, the m. And then if we have a molarity as a concentration expression, we have another practical activity coefficient, which is the gamma c. So A equals gamma c multiplied by the c, which is the concentration in molar scale. And then if we have the molar fraction scale, then we will get a rational activity coefficient, and A equals to gamma x multiplied by x, which is the mole fraction in this case. Now in this slide I'm going to talk about an important parameter that is more frequently used in the development of pharmaceutical formulations, which is the ionic strength. So an important question: why do we need to account for this parameter? Why do we need to use it? To answer for this question, as I mentioned previously, that we are dealing with mixtures of different materials in the solution, and I mentioned before that we are using the concentrations, different expressions for the concentration, to express the number of particles or ions inside the solution. But then I mentioned later on that this is not only the important thing inside the solution. We do have the charge as well for the ions. It's also important, and at the same time, if we have some ionic interactions, like by the electrostatic attractions between the ions, these also affecting the properties of the solution. So in order to account for both the number of ions and the charge of the ions and the electrostatic attractions between the ions, we are using the ionic strength, and this parameter is introduced by Debye-Hückel just to account for all these things inside the solution. So it's more expressing the activity of ions inside the solution compared to the concentration expression. Now the other important thing is how to calculate the ionic strength. After explaining the importance of this parameter, now we need to know the method of calculating the ionic strength. So the ionic strength, the mu, is equals to half multiplied by the sum of the concentration multiplied by the valence raised to the square power for each ion inside the solution. So what we are going to do is to multiply the concentration by the valence raised to the square power for each ion, and then get the sum of all the ions for the different ions inside the solution, and then divide the sum by 2. So in this case we are accounting for the number of ions and the valence, and at the same time for the positive ion, negative ion interaction inside the solution. That's why we are dividing the sum by 2, because if we have positive ions and negative ions, they will be interacting together by the electrostatic interactions. And this example shown in this slide will show you how to calculate the ionic strength for the individual ions, as you can see, for 0.01 molar KCl or 0.01 molar BaSO4 and for 0.01 molar Na2SO4. So from these you can know exactly how to calculate it using this equation for the individual salts, and then if you want to put all the salts together you can calculate the ionic strength for the total number of ions inside the solution. So from this you can get more expressing parameter, because it's accounting for what? For the concentration of ions, and then for the charge, because the monovalent ions are not behaving the same as the divalent or the trivalent ions, and at the same time you are accounting for the electrostatic interactions between the ions. So that's why we are using this important parameter, what we call it the ionic strength. So at the end of this lecture, I hope that I managed to cover all the things related to the solutions of electrolytes, starting with the colligative properties of pharmaceutical electrolytes compared to solutions of non-electrolytes. So I explained the differences between the solutions of electrolytes compared to the non-electrolytes, and how does the electrolytes affecting the colligative properties inside the solution. And also I also talked about drugs and ionization. So what we are dealing is compounds that can be ionized inside the solution. So drugs, still chemical compounds that can be positively or negatively ionized inside the solution, and also the majority of these drugs are weak electrolytes. And then I mentioned some information about the degree of dissociation. With the strong electrolytes we have complete ionization, complete separation of the ions, but then with the weak electrolytes, and that's the majority of the active pharmaceutical ingredients, they are partly dissociating, and that's why we have this equilibrium arrows that indicates we are following the dissociation until we reach the equilibrium status, in which the ions the ions are in equilibrium with the non-ionic or the non-ionized form of the drug or the excipients. And then we moved to talk about the activity and the activity coefficient, and why do we need to express these into activity? Because we are dealing with anomaly in case of electrolytic solution. It's not especially in moderate and high concentration of strong electrolyte, we have deviation because of the electrostatic interactions between the ions. And finally I introduce an important parameter, which is the ionic strength, and the ionic strength is actually expressing the solution of electrolytes in terms of the number of ions, the charge of the ions, and at the same time the electrostatic interaction between the ions. So I hope that everything is clear, and please, if you have any question, don't hesitate to contact me or send a question on my email, and thank you for listening.